I welcome you to today's class as we continue looking at Hooke's law and deformation. And today we're specifically going to look into the deformation graphs. And for the purpose of this class, we'll only do two types. So we have two main objectives. By the end of this class, you should be able to interpret force extension graphs and also interpret extension force graphs, and finally solve problems involving deformation graphs. So let's quickly dive into understanding and interpreting graphs. I'll start with the force extension graph. We said the Hooke's law specified that force is directly proportional to the extension. In our previous class, we said force is directly proportional to the extension. Then we emphasized that Hooke's law is dealing with a linear relationship between force and extension. So we expect a graph to be a straight line as long as they are directly proportional. And we moved on to talk about proportionality. And we said since it's linear proportional, it must be starting from the origin of the graph. So when we are to draw force extension graph, there are key things we need to know. The limit of proportionality is the key point. Before the limit of proportionality, there is a linear relationship that is proportional, meaning it's passing through the origin at point 0, 0. Beyond the limit of proportionality, we don't expect to see a straight line. But as long as we're within the limit of proportionality, we should represent Hooke's law using a straight line. Where is this line coming from? From the origin, because it is directly proportional. Once we go beyond the limit of proportionality, we expect a curve or a non-linear relationship. Now, it's very important on this part to note that the point where the graph changes from its linear relationship to a curve is what we call the limit of proportionality. I'm not going to define this. I defined it in the previous class. If you have not watched the previous class, revisit the previous class on this channel. Now, let's look into the force extension graph. It should be starting from the origin, because when the force is 0, the extension also must be 0. And before the limit of proportionality, we expect the force to be directly proportional to E. Hence, it's characterized by a straight line. It is a linear relationship. That's how Hooke's law defined it. Now, when we reach this point where it's now starting to be a curve here, this is the point we call the limit of proportionality. The extension beyond which the relationship is no longer directly proportional, beyond which force and extension are no longer directly proportional. Remember to define this, it's a key requisite for your syllabus. Then the graph becomes non-linear. I want to emphasize for the shape, when we reach beyond the limit of proportionality, take note of the axis. If it's a force extension graph, it should be bending with decreasing gradient, a gradient that is going towards 0. Meaning you need a small force to cause a very big change. A small force causes a big change. In other words, it's now easy to stretch. This is very, very important. For a force extension graph, we should have a curve whose gradient is decreasing towards 0, signifying that a small force will produce a bigger extension and the material has become easy to stretch. Let me talk about the gradient property of a force extension graph. As long as you are within the limit of proportionality, the gradient is always equal to the spring constant. The gradient is equal to the spring constant. The gradient is equal to K. We can justify this using analysis of units, since we did the dimensional analysis of units. The gradient is written as a change in y divided by a change in x. What do we have on the x-axis? We have a force. Sorry, on the y-axis we have a force. What about on the x? We have extension. So what are the units of gradient? The units of gradient must be equal to the units of a force divided by the units of extension. And we noted that this is a Newton and this is a meter. What is a Newton per meter? This is the unit of spring constant. So our gradient is always equal to the spring constant. You will get questions like, use your graph to determine the spring constant. They won't say calculate the gradient. They'll say use your graph to determine the spring constant. What do? You use this gradient property. The gradient of a force extension graph gives us spring constant. I'll use an example to solve this problem. But let me just look at another graph, which is the extension force graph. The extension force graph is an inverse of a force extension graph. We have inverted the axis. So the extension force graph is an inverse of the force extension graph. So we expect it to be an inverted version. So it being directly proportional, it starts from the origin. When the force is 0, the extension is 0. And it will be a straight line provided the limit of elasticity is not yet exceeded. We expect this relationship to remain linear. Now, beyond the limit of proportionality, we expect a curve with increasing gradient. A curve with increasing gradient. It's an inverse. For a force extension, the gradient was decreasing. This is force extension. But for an extension force, we expect an increasing. The tangents should be getting steeper and steeper. So this is what I wanted you to note. Now that this is an inverted graph, we don't expect the gradient to be the spring constant. So gradient is not equal to the spring constant for this graph, because this is an inverted graph. However, the spring constant is the inverse of gradient. How do we calculate gradient? Change in y divided by change in x. What do we have on the y-axis? We have a meter, because it's extension which is measured in meters. What do you have on the x-axis? We have a Newton, because it's a force that is measured in newtons. Now, a meter per Newton is the inverse of a Newton per meter. So if this is the inverse of this, we can safely say the spring constant is the inverse of gradient. Let's solve problems and see how we apply these techniques to solve graphs of deformation. Here is practice question number 1. I will give you this question, take a break, try to attempt it over the break. After the commercial break, then I'll give you the solution. Enjoy your time. Welcome back. Let's try to solve this problem. Fig 2.1 shows an extension load. Key things before you answer any question so that you don't make mistakes. Look at the axis. There is extension which is expected to be in meters. There is a load which is a force. We expect it to be in newtons. So this is going to give us change in y divided by change in x, which is a meter per Newton. So the inverse of this gradient is going to give us the spring constant. but the gradient itself, gradient G, is not equal to the spring constant because it's an extension load graph. Right, let's answer the questions from the past paper. The point of the limit elasticity is P. So up to P, there is a direct proportionality between extension and force. Let's answer item 1. Name the law obeyed by the spring from the origin to P. From the point OO to P, there is passing through the origin and it's linear. Hence, it's directly proportional. And this is Hooke's law. F is equals to KE. So here we can safely say the law is Hooke's law. Why? It's passing through the origin and it's what? A straight line. Hence, we can safely say it's obeying Hooke's law. So which law is being obeyed there? It's Hooke's law. Provided the limit of elasticity is not passed, force and extension are directly proportional. Describe two features of the graph which shows that the law is observed. I've already answered this. Number one, it is a linear graph. A straight line is showing that the one is increasing with the other. Number two, it's passing through the origin. Passing through the origin. It's passing through the origin, meaning if the force is 0, the extension is also 0. Therefore, we can safely say it is obeying Hooke's law because of these two things. Number one, it's a linear relationship. Number two, it's passing through the origin. Part B says, on Fig 2.1, sketch a possible continuation of the graph when the spring is loaded beyond the limit of proportionality. We said there are two curves. If it is a force extension graph, origin up to the limit of proportionality, then from there it becomes a curve with decreasing gradient. The extension force graph is the inverse of this, so we expect it to continue with increasing gradient. That is the sketch expected of you. I'm going to leave you with a question for practice. I'm going to leave you with a question for practice, and I'm going to put the answer here. We expect you to find 2.5 newtons per millimeter. Try to solve this problem and find 2.5 newtons per millimeter. Today's class closes here. Chigo, the senior coach, signing out. Enjoy your day.